Sounds great. Thank you.
Thank you. Okay, this is Suresh Vafai-Tawar. I will be the coordinator of this section of Winter Seminar Series. We have Dr. Alex Lam, a senior researcher at Microsoft. He earned his Bachelor of Science in Johns Hopkins, and also his Master and PhD in University of Montreal. Previously, he worked at Google Brain and also Amazon. I briefly explained the logistics of this section. Afterwards, we will have Dr. Okay, we have 1 hour, and also for asking your questions, there will be a Google form, which is in the chat box in the right, which will be pinned. So if you have any question during the section, please ask, and at the end we will answer them. Doctor, this is all yours.
Thanks a lot. I'm Alex Lam. I'm presenting Discovering Agent-Centric Latent Dynamics in Theory and in Practice. So just to motivate things, let me see if I can play this video of a spider. Oh no, it's playing an ad.
Silent and your beautiful music. Oh yes.
I'll see if this spider plays.
Portia is a genius. She can map her world in 3 dimensions and
Can you hear me?
formulate a plan of attack.
Does the audio not come through, I guess?
Yes. We are seeing the PowerPoint app, not the presentation.
Oh, sorry. Oh, 1 sec. Should I just have it zoomed out like this? Let me see.
It's okay. There's no problem.
Okay, great. Yeah. So to motivate this research project, we had a video, but the basic idea is there's this small animal called a jumping spider. It's about the size of a human fingernail, but this little spider, and its brain is about the size of a single grain of sand. But this spider has some fairly sophisticated capabilities, and it hunts other spiders as its way of making a living. So it has some advanced capabilities. So it's able to plan. It can see a location it wants to get to. It can figure out a trajectory and execute how to get to its desired goal point. It's capable of localization. It's able to use its sensors to figure out where it is in the world. And how much it explores is maybe an open question, but it has some ability to map out the world by gaining experience. And this issue is related to real-world simultaneous localization and mapping, or SLAM. And the basic idea is if we have an agent that has rich sensors and can move around the world, can we use that to have an agent which has a map and an understanding of the world? So this sense making is an important engineered ability in robots, but we could ask ourselves, what if the sensors or actuators are damaged but still somewhat functional? What if a new sensor is plugged in? What if we want to do a task that's not navigation? Or what if we want something more complicated, like a software agent? So we really want a learning approach for our robots and agents to be able to make sense of themselves in the world. So what are some things that make the problem unique? Data and interaction are 2 sources of training signal. So we could either imagine having an offline data set or having the ability to interact and gain experience in the world. How do we define rewards and goals for our agent is an interesting question. Additionally, learning to control a system can be much easier and much cheaper than learning a generative model of the entire system. So if you think back to the hunting spider that we just looked at, there's no way that this hunting spider is learning a full video generative model of its world system, at least as far as I can tell, because I don't see how it could have the computational capacity to do that. Additionally, if you think just intuitively as a human, you have the ability to make sense of where you are in the world and build a state, but you don't learn like the full ability to generate, videos of your own, let's say, sensory inputs. So another motivating point I'd make for learning latent states for agent dynamics comes from the specific example of a video game called Zelda Link's Awakening. So there's something very interesting about this. So this game, Zelda Link's Awakening, had a 1998 release, and you can see a screenshot of it on the left. And that release was only 8 megabytes, but it had a 2018 remaster with much more sophisticated and detailed graphics, but essentially identical gameplay. And this new version of the game is 8 gigabytes. So the game file is 1,000 times larger. And you could imagine that if you have to learn a generative model of, images of things from this game, it's possible that it's hard to be 100% sure, but it seems very feasible that your generative model has to be 1,000 times larger. But the agent-centric state is basically exactly the same thing. And you could imagine the intelligence that you need to play one game or the other game is basically the same. So the central question of the research program here is, how can we reverse this arrow? So another way we can ask this is, what is a minimal sufficient set of values enabling an agent to do all the things in its environment? So it's not classification. The set of latent states is not defined beforehand in advance. It's not clustering, because most of the clusters you'd end up with would be irrelevant. And it's not generative modeling, because there's a massive information discard that's required. So we basically want to go from something with a huge number of bits, like this visual stream, into something smaller that captures the key pieces of information. So I don't know if this video has a chance to play, but one example we have has I don't know if you guys can actually see the video playing.
Yeah.
But you can.
Yeah, we can.
Okay. Oh, great. Thank you. So in this experiment here in our Microsoft office in New York, we record a video of this robot moving around under random policy. And it's in front of a TV playing a video, and you have all these distractors going, and we're able to learn a representation such that if we map the representation back to the observation space, the information about the video is completely removed, while the information about the robot arm itself is completely preserved. So let me try to formalize this setting a little bit more. So we're going to define a latent state, or sometimes we'll call it an agent-centric state, Z, or I know some places you call it Z. And then we're going to have some agent-centric dynamics. So it's a probability distribution, or could just be a deterministic function, which takes Z and A and maps to some Z prime. There's also going to be what we'll call exogenous noise. I think it's an eta. And then we're going to assume that this follows its own decoupled dynamics. And then we're also going to assume that on each time step, the observations are going to be produced as a disjoint function of the agent-centric state on that time step, Z, and the exogenous noise on that time step, eta. And then we also have to make an assumption that's called the blockwise disjoint assumption, which basically says that each value for O for the observation can one or some values of, or one value of Z or eta. It can't be produced by multiple values of Z and eta, but it is possible for a value of Z and eta to map to different possible observation values. Let me see. So, yeah. Okay, so just to give a little bit of terminology, a little more terminology here, we're in a setting where there's an agent that takes an action A in the world, and we receive some observation O. And the observation, in pretty much everything we're working with here, the observation is going to be an image, but it could be more general than this. And then the policy is a function which we generally learn, which will map from observations to actions. I'll also quickly say that this setting is called the exogenous block MDP setting. And if there's no exogenous noise, then that's just called the block MDP setting. Okay, so now that we've established this setting, this exogenous block MDP setting, there's something that's very cool that happens, which is, in deep learning, we have, and I guess maybe even before deep learning, we have all of these different objectives that can be used for learning representations. So you have a whole zoo of different representation learning algorithms. But what's very neat is when you're in this specific setting, you can make concrete theoretical claims about which types of objectives learn a sufficient or an insufficient representation. And what we'll see here is over on the left, we have some ways of learning representations, which we're going to claim capture too much information. So they'll capture information about the observation and the exogenous noise. They'll capture more than the agent-centric state. We have a solution in the middle, this multi-step inverse with self-prediction, which we claim, I guess under some conditions, will capture just the agent-centric latent state. And then on the right, we have some approaches that maybe capture too little information or won't capture the full agent-centric latent state. So let me go into some of these in a little bit more detail. So one approach is just learning from a reward function. And I guess there's many papers on this, but one I'll look at is the mu0 paper by Schrittweiser. And the basic idea there is we're going to learn a value function using this Monte Carlo tree search backup. So we're going to use a neural net to learn a sort of value-centric latent state. So what's wrong with the representation that we learn? Or, well, what's good about it? What's good is it could be very concise and good for a particular task. But a downside is that it's task-specific. And additionally, it may perform poorly if the reward is hard to find. Another approach is autoencoders. So here I reference David Ha and Jürgen Schmidhuber's World Models paper. But the basic idea here is we take an observation, we encode it into a latent state, and then we decode it back to, let's say, our image. So it's very simple. What's good about it is if you're in a Markov setting, it's definitely a sufficient representation, but it seems like you're basically just going to capture everything. So even if there's just noise in the observation, you're still going to get that too. And then it's also kind of questionable how much you can really compress the input. So JPEG compression is on the order of like 10-to-1 compression. So in this setting, we're maybe hoping that we can achieve better compression. Additionally, with the autoencoder, you have to learn the emission function, and that could turn out to be a complicated function to learn. There's another approach that's called temporal contrastive methods. And if you've seen stuff like CLIP, for example, it's a little bit like this. Info and CE is a bit like this. But how does this work? The basic idea is we're going to turn our representation learning into a classification problem. And our positive examples are going to be true pairs. So observation, action, next observation will be a positive pair. And then our negative pair will be observation, action, and then a random observation from somewhere in our data set. So you could imagine you have to learn something about the observations in order to do this, this classification well. And my colleague Dipendra Misra proved some theory about this in 2020. So what are some good things about this contrastive latent state? One is if you just think about the information processing inequality, this should be the same size as the autoencoder representation or smaller. Additionally, it doesn't need to encode the behavior of the agent. It's a simple learning objective. And this paper by Dipendra Misra called the Homer paper showed the sufficiency of the contrastive learning objective. So one of the issues with the contrastive learning objective is that you capture these exogenous noise and these background distractors. But another very serious practical challenge is the fact that most negative samples, remember, if we just draw our negative samples uniformly, almost every negative sample can be basically trivially rejected because you could just find one thing that shows that it's a negative sample. Like if you just find one little inconsistency. So what tends to happen in practice is you either have to apply some tricks to try to make this work a little bit better. Like you make the you don't use the next frame, but you use like a few frames in the future. Or you could try to mine some hard negatives. But in practice, it becomes a little bit hard to get it working really well. There's another, just turning to another approach for representation learning, which we could call self-prediction. So the reference I give here is the Biol Explore paper by Guo in 2022. Now, there's actually been a lot of work on this. I know Jan LeCun kind of makes this one of his key. This is something that he advocates for a lot these days, and he markets it under a name called JEPA, which I think is like Joint Embedding Prediction Architecture. But let me just say what it is, because it's kind of an interesting idea. And the basic idea is we're going to take our observation, encode it into a representation, and then we're going to predict our model's own representation at some time step in the future. And then typically, the target network could be like a moving average of the network, and typically will only backpropagate through the side that's doing the prediction, and we won't pass gradients into the target network. But there's many variants of this basic idea. So one of the nice things about this is that it seems to work empirically. And additionally, it seems like there's mechanisms to handle partially observed settings. But if you just look at this objective, there's kind of an obvious limitation here, which is, let's say we just set fs to 0 or to always return a constant. Then it's very easy to minimize this loss in kind of a trivial way. Although there was a paper, Tong 2022, which does provide some explanation of why it doesn't collapse. I think maybe the deeper issue here is a lack of a clear theoretical understanding of what this type of approach will or won't learn. And in my opinion, maybe this is a good thing to work on in the future, because maybe there is a way to establish a nice theoretical understanding for what this learns. But I think that's something that still has to be done. So another approach for learning representations is something called an inverse model. Sometimes you could call this inverse dynamics or inverse kinematics. But the basic idea here is we'll take the observation on a time step, the observation on the next time step. We'll encode both of these, and then we'll use it to predict the action that we took from between these two time steps. So what's good about this is, first, you can ignore distractors. It doesn't seem like it has to encode the behavior of the agent. But as we'll show, it's not sufficient to learn a good representation. And why it's insufficient is kind of interesting. It's something that we should go into. But first, let's just try to get a little bit of intuition for what this objective learns. So here I drew a little MDP with just 9 states. And your actions are just, you can move in these different directions. So up, down, left, right, blah, blah, blah. It's kind of like you have a bridge here running down the middle. Now let's say I just collect a lot of samples under this, and then I do supervised learning to predict the actions. So if I say 1 to 2, the predicted action will be the right movement action. If I say 5-8, the action label is down. If I say 9-8, the action label is left. Yeah, so the inverse model turns out to not quite work correctly, even in this setting. So basically, you can get the same accuracy in action prediction, even if you take these two states in the middle and assign them the same representation. So basically, what happens is if you train with a one-step inverse model, if you have any pair of states which are 2 or more steps away from each other, and those two states kind of have the same local topology, the model has no incentive to map them to distinct representations. It could map them to the same representation. And indeed, there's something very cool that happens, which is we sort of had our robot here simulate this simple synthetic environment, and we plot out a confusion matrix for what the representation learns in the worst case scenario, which is that it sort of aliases these three states together. And indeed, if we collect the data, video from this real robot, and we train a simple inverse model, it's kind of cool. The actual confusion matrix that you get empirically looks kind of similar, or looks very similar, to this theoretical worst case. So let's see. So one of the things we've done is we've developed this multi-step inverse model by myself and my colleagues in 2022. And it turns out to be a very simple modification of the simple inverse model. And the basic idea there is you'll roll out in your environment for k steps, and you'll just predict the first action that you took as a function of your first observations encoding and your last observations encoding. What's good about this is we can ignore distractors. We can encode, we don't have to encode the behavior of the agent, and it seems to be sufficient, but it doesn't deal with POMDPs. So why does this work well? Basically, what happens is we're able to separate out states that are far away, because any pair of states will appear in these multi-step inverse model examples under some assumptions related to reachability. In particular, we have to assume that there exists some time step t such that any state is reachable from any other state in exactly t steps. So that actually does rule out some MDPs where there's like an uncontrollable periodic structure. But there was a nice paper by Alexander Levine, Texas, that showed that if you combine multi-step inverse models and self-prediction, it's possible to remove this assumption. Additionally, if we're willing to assume that the exogenous noise is weakly correlated, we can recover the agent-centric state uniquely up to permutation. Otherwise, we just have to stick to showing that the state is usable for planning and exploration, but could be non-unique. And additionally, in all of this work, we have to assume that the latent dynamics are deterministic, although there's some other work by our group on relaxing those assumptions. Yeah, so this approach turns out to at least in this environment, learns the full agent-centric state. So we can see empirically what we get is very similar to the theory worst case prediction. Yeah, so with everything we've done so far, this lets us return to the picture that we had originally, showing all of these different objectives for latent state discovery. So some of the key points are causal summarization is a key empirically tractable problem. You could have a problem with a simple latent state that can still induce complex observations. And we hope to be able to show that different objectives give us a library for being able to control what information is saved or lost in our representation. I want to go into a little bit more detail now on this multi-step inverse model. So there's something kind of interesting, which maybe happens in a lot of reinforcement learning, but you have a bit of a chicken and an egg problem. So high quality data allows us to learn a latent state that captures the agent-centric state and ignores exogenous noise, which is what allows us to have a high quality model. And the high quality model will allow us to construct a good data gathering policy, which has high coverage, reaches goals successfully, and ignores exogenous noise. But it's kind of tricky to start from nothing and then build these two things together. One thing I want to look at for the multi-step inverse model is the proof that we're able to ignore exogenous noise is very simple. So I just want to look at it real quick. And basically the idea is if we write out this action prediction in terms of the observation at time step t and the observation at time step t plus k, the first thing we can do is we can apply Bayes' theorem on OT plus K and AT to just swap the order of these. And then we have a marginalization out with a different action in the denominator. And then after we've applied Bayes' theorem, we can, unroll the dynamics according to our decoupling assumption. And then once we've written this out, the emission function cancels in the numerator and the denominator. And then also the exogenous dynamics cancel in the numerator and the denominator because it doesn't depend on the action. So we're left with this as our Bayes optimal classifier. Another thing I want to comment on is the ideal policy in theory. So in theory, we pick goals to get high coverage. And for a goal, we can take a single random action and then follow the optimal policy to reach the goal as quickly as possible. And in some ways, it's a little bit like a speed running policy that you can think of like with video games. And why is this sufficient? So if we think about the multi-step inverse model predicting the action from our initial state ZT and our goal state ZG, the fact that we sampled over goals and reached them effectively means we get high coverage over ZT and ZG, and just the single random action that we take initially gives us high coverage over the action. So some of the elements necessary for success are a flexible and minimal representation. So we tend to use like convnets, vision transformers, or mixer architecture. And the VQ bottleneck can be used to make the state minimal. We use the multi-step inverse objective, or we use it together with self-prediction. And then we also need a high quality data collection policy. So one thing you can do with this is you can, we consider rolling out in this environment called forums, and we modified the environment so that there's a certain action which takes the agent back to this initial starting point in the top left corner. And if we roll out under random policy, the agent just gets stuck in the top left corner. But if we use the AC state algorithm to explore, we're able to achieve high coverage in a reasonable number of samples. Additionally, we considered a noisy first-person view environment called Matterport. So basically there, the agent receives these first-person views, and we're in a setting where the camera will kind of rotate up or down randomly as the agent is moving. And basically all of the approaches we try do a good job of recovering the controllable state, which is the position and orientation of the agent. But only the AC state with the bottleneck is able to remove the distracting information about the height of the camera. So another paper led by Riyashad Islam, very closely related to this, is we tried the multi-step inverse model for offline RL. And here we took just common offline RL benchmarks. We encode the observation at time step t, encode the observation at time step t plus k, and we just use a small MLP to predict the action. And then these representations are used for a standard offline RL algorithm. I think in our case it's Dr. Q. And what we see here is even in the settings of very complex, distracting exogenous noise, like having a video in the background, for example, Acro is still able to attain high returns, even though it's difficult for many of the other representation learning algorithms. There's something else that's very interesting that we discovered in this paper, which is if you collect data under a completely random policy, like the agents just take random actions, then this multi-step inverse model Acro is still okay. But if you do behavior cloning, their performance is almost trivially bad. Like it gets no reward, basically, which makes sense because you're just predicting something random then. But if you have a deterministic expert policy, behavior cloning and the multi-step inverse model are both pretty good. So one way you could think about it is the multi-step inverse model can help learn better representations in cases where the quality of the policy is suboptimal. Another thing that we've looked into is not just the correctness of the state in the sense of aliasing the states, but also thinking about how the states are shaped. Like, can we get them to obey a metric space? So here I have an interesting experiment where I train the multi-step inverse model. And this is just a maze. It's basically like a spiral maze. The agent can move around with continuous actions and have a continuous state. And if I train the multi-step inverse model, I can get it to be the case that the agent's true state is exactly recovered. Like I can just confirm that via probing. But then if I do a k-means clustering of our learned latent state, you can see that it doesn't respect the walls at all. And, if the agent, it's kind of interesting. It almost likes to group together states that are kind of functionally similar, like states where we're both right on the left side of a wall. So if you want to do any kind of geometric abstraction, that's not ideal. So one thing that we did is we tried taking the representation learned by this multi-step inverse model and then using contrastive learning to learn this sort of local neighborhood structure on top. And then this lets us learn a state that basically has like a perfect structure. And actually, I think this was a paper at ICML last year, but it makes me wonder if you trained with one of these self-prediction objectives, could it also learn this nice local neighborhood structure? And indeed, one thing we see, which is kind of nice, is if you learn with this, it's substantially easier to use PPO on top to get this goal-seeking behavior. So that's nice. Another paper we have along these lines, which is recent and which is kind of closely related, is can we use an objective which is inspired by the multi-step inverse model to enhance the representations learned by transformers, basically in the context of like large language models, so like a very standard setting. And it turns out to be the case that you can actually do something very simple and provably get some kind of nice benefits. Okay, so the basic idea here is in our normal autoregressive transformer, we have a forward running, and I call it an encoder network here, but it's normally called a decoder in a transformer. But I'll basically take x1 to xt, and then I'll predict xt plus 1. And that's basically being done for every step. So in our proposed modification, imagine you have a forward running encoder in time, and then you also have a backwards running encoder in time. And now imagine you take every pair of representation from the forward encoder and the backward encoder, concatenate them together, and you're going to predict two things. You're going to predict the one token prior to the start of the backward encoder, and you're going to predict one token right after the end of the forward encoder. So you basically have these two prediction tasks. And there's something that's very cool about this, which is you can write an autoregressive decomposition of the backwards, these backwards, I guess you could call them observations or tokens. And then you can show that this belief state transformer learns a representation in the forward encoder that lets it solve every possible problem or every possible previous token prediction problem with the backward encoder. And that will cause the representation in the forward encoder to become a compact belief state on every time step. And the same argument will apply in reverse for the backwards encoder because it's kind of symmetric. So we'll basically achieve the property that our final representation in the transformer should optimally have the information for predicting the joint distribution over all future tokens. And that's more of what we're working on these days. Some thoughts on future work is I think these self-prediction methods that I talked about earlier have become very popular for learning representations, including for actions. So we could imagine applying them over the set of all YouTube videos, or really any setup with natural sensors. And Jan LeCun is a heavy promoter of the self-prediction framework. So I think it would be interesting to see if the theoretical ideas about these agent-centric latent states could be used to prove some theories about self-prediction. And I think you're never going to be able to use this type of method to ignore all distractors like we were trying to do in this work. But I think you still can get away with not having to render your representation into the pixel space. And I think there could be a lot of savings in not having to learn that emission function. And then I think we might also be able to analyze or prove some theories about what kinds of signals the self-prediction model likes to learn. So, it's interesting to me that, there's certain things as a person, you can look at them and you can say, oh, this is just like a random noisy pattern, or this isn't very meaningful, and you can kind of just ignore it or not focus much on learning it. And you can sort of focus on things that are easier to predict. So I guess formalizing that concept could be interesting. It's a little out of date now, but here I have a collection of some of the people that I've worked with on this effort. And here's a collection of some of the papers involved. So with all that said, I'll leave the last, 15 minutes for questions.
Thank you very much for your great presentation. And do you have my voice?
Yes, I hear you.
Thank you. Okay, regarding the first question, he asked, it seems that we are looking for a method of compression. Shouldn't we focus on compressing a mechanism instead of observations? For example, focusing on difference of continuing observations, somewhat like Bill.
Is there any way I can see it, or I can try to answer, but did you say focus on the sequence of observations like Biol?
Yeah.
Biol is a good method. One thing that I would say is in this work, I was mostly focused on the, I guess I call it like the Markov decision process setting, or the setting where you assume that one observation is sufficient to decode the state. But definitely in general, it's good to focus on the partially observable setting, or where you're trying to compress down a sequence.
Okay, thank you. Another participant asked that can Williams and LMs help us in learning agent-centric states?
Can you repeat that?
Okay. He asked that can VLMs and LLMs help us in learning agent-centric state representations, or at least help us remove the noise from these states?
Oh, yeah. Let me think about that a little bit. So, so if that means like a pre-trained VLM or a pre-trained LLM, that's a very interesting question. So my understanding is LLMs in general are pretty good at removing like obviously distracting pieces of information in a text stream. In terms of VLMs, that's probably also true that they're getting to be decent at removing things that are obviously distracting. I guess for me, I almost think like these kinds of algorithms should be useful in learning VLMs. So like my impression is that algorithms that are related to BEOL, like Dino or Dino V2, are used in learning the encoder for the VLM, or to get the representation for the image. So I feel like better representations for learning the states should be part of the process of learning the VLM. So I think that's my answer.
Okay, thank you. Okay, the next question. How would you define a supervision which separates environment noises from the distraction noises?
I'd have to think a little bit about what's meant by environment noises and distraction noises. I mean, I guess it's interesting. In some sense, I guess you could say that the stuff on the multi-step inverse model removes distractions if you just define distractions under this decoupled dynamics framework. And it is kind of nice because the multi-step inverse model is kind of like a supervised setup, although the actions could be kind of noisy. So maybe it's maybe not always the nicest supervised objective where you have like a very clean label. Let me try to find one thing real quick. One of my colleagues, Manan Tomar, has a paper where he uses an information gating objective to explicitly produce a mask over what parts of the image, I posted in the chat, over what parts of the image are considered like distracting or non-distracting. And at least on Mujoko, the masks are pretty intuitive. So I guess in some sense that could be used as a label. But I think it's a good question. The next question, maybe?
Thank you. The next participant asked that I couldn't clearly see the inductive bias that you used for the compression, which is specific to the MDP settings. The inductive bias were somewhat immature and similar to other fields, for example, the contrastive learning methods.
Yeah, so it's a good point. In terms of bottlenecks, one thing I used is the vector quantization bottleneck, like VQ bottleneck. There's another thing that's called the Gaussian information bottleneck. Yeah, there might be a paper that's called like deep information bottleneck. From a conceptual point of view in this work, when we analyze it in theory, we just say like the encoder is like a black box function, and then we just talk about how many states can be represented by the output of that function. So that makes the most sense when the function has like a discrete output. So there's only so many output states it can have. And then we usually don't dive into like the actual, let's say, structure of the function. If others in the field of like contrastive learning or self-prediction have studied this in a deeper way, that would be interesting to me. I'm not aware of it, but if that is out there, that's kind of that would certainly be interesting to me. I mean, I know there's some implicit bottleneck just induced by the dimensionality of the representation, but if it's been studied in a more detailed way, that would be something I'd be curious to see.
Okay, thank you. The next question, isn't what you did in the maze example contradictory to your goal? In Zelda, you explained that the mechanisms are the same between the two environments, but the details are different. So the action that we choose is more important.
Oh, sorry. I couldn't hear in that. What example is it referring to?
I think the Zelda game that you first explained.
Oh, Zelda. Yeah, yeah. Oh, sorry. What was the next thing then?
I think he was referring to the maze problem, that the states were similar, even though there were vowels between them. And he's referring to the Zelda that you said the mechanisms are important. So the action that we want to go down is more important than considering the details of the walls and such things, I think, what he meant.
Yeah. Yeah, so there's a little bit of a shift in motive, or there is a little bit of a discrepancy here, because I guess hypothetically, if we trained our multi-step inverse model on this Zelda game and we got it to be extremely good, it may have a representation that's even smaller than the game file from this original game. So there's certain things like, I don't know, the fact that I have a drawer, or the fact that this floor has some pattern, which really isn't even strictly necessary for an agent. Maybe the most minimal representation is just going to make it look like a maze or something. But I kind of think if you were learning a representation like a self-prediction, like a Biol type objective, you'd still want to learn a little bit about, say, what this background looks like or what these other characters look like. But maybe it would be something more minimal. So it would look a little bit more like what you have on the left, or maybe even a little bit more minimal than that. I'm not 100% sure if I understood the question correctly, but that's... Hopefully I was close.
Okay, thank you. And the last question is that I think he's referring to the slide that you explained, the transformer solution. He said that the transformers doesn't the transformers capture the noises too much?
Oh yeah, that's true. So in this belief state transformer paper, we're not concerned with anything like noise or distraction or anything like that. All we want to do is we just want to have a representation that captures all of the capturable information about the future time steps. It's kind of interesting. I guess, like, with this work, we wanted to have something that was more applicable to the general, like, language modeling type setting. And there, I think, assuming that you have like this structure where there's actions and observations, reduces the applicability of it, because maybe I guess in a typical language modeling setting, you just assume a list of tokens and you don't have that kind of decomposition.
Okay, thank you very much. I think the questions are now finished, and the presentation was very high level, and I enjoyed it a lot. So,
Oh, thank you.
yeah, we hope that we have you in the next years in the WSS.
All right, awesome. Thank you.
Thank you very much. Have a great day.
Bye.